Fantastic. Let us start. Exciting. First meeting, computational geometry. Always fun topic, fun course, I think. It's combined CS, grad and undergrad. Really one of my favorite courses. My main research area, career, my research is there. Tons of beautiful problems, practical, relevant to many topics, relevant to robotics, relevant to image recognition, relevant to machine learning, classification, nearest neighbor, resource allocation. It's like a computational geometry is like a huge meta course with plenty of other tiny domains living underneath it, like artificial intelligence and VLSI designs and vehicle routings, and we'd like to say that all the answers are already existing in computational geometry and you just need to find the right papers. But okay, let's be serious. Okay, bureaucracy about this course, bibliography. We are using 2.5 major books in this course. The deeper among the two, the one that goes a bit deeper is the famous book by the 4M or MMMS. It goes by Mark de Berg, Mark van Creveld, Mark Overmars, and Ottfried Schwarzkopf. And when Ottfried is saying it, his joke was that it's Mark de Berg, Mark van Creveld, Mark Overmars, and myself, so it's 4M. There are actually, I think, need to update. There is a third version. You can access it electronically from the library. Actually, I placed a link since it's fine with the authors. I actually placed a link to the PDF from the course website, and that's one of the books. And the good thing about this book is that it doesn't take any shortcuts. It doesn't assume that input is not nasty, in a sense. As we will see very soon, if I look for an algorithm that looks as an input intersection of 3 segments and find the intersection points of the intersection points of these 3 segments, it makes life way easier to assume that that there is no point that lies on all 3 segments, that every pair intersect only inside this pair but not with others. And the algorithm is somehow more friendly, and it's somehow a special case if the third segment just stabs them exactly in the very same point. So the 4M textbook, beside being deeper mathematically, also don't assume any such shortcuts. That's a good point. When the bad point is that, of course, that it doesn't take any shortcuts. So sometimes the explanation are, I'd like to explain things as a 2-step process of let's first make some shortcuts, see what the essence of the algorithm, and only then, if we want, talks about the non-general case, the special cases, and I'll prefer it in this aspect, but the textbook, this textbook does not do it. Anyhow, it's extremely popular. You can get. Let me close the door, please. Guys, recording. So O'Rourke has two related textbooks. One is computational geometry in C, and one is computational geometry, and it's very nice textbook, more common somehow in undergrad version of the course, but beautifully explained, and the topics are quite similar. There is not much that will study that exists only in the 4M books and does not exist in O'Rourke's book also. O'Rourke, by the way, is a fantastic character that deserved world championship for being one of the big experts of origamis, both as art and as mathematical puzzles. And actually, he and Eric Demain have a book, wrote a book about origami pretty recently. Dave Mount has his fantastic lecture. I'll use his slides here and there, and I'll also will give access for you to his class notes. He's very coherent, very clean explanation, and ridiculously smart. Craig Gottesman used to be at the Technion, now in New York and GIT. I'll use some of his slides that I modified, so it's also a good chance to say thanks to him allowing me to share his slides as well as other slides of Dave Mount that I'll share, as well as my own slides. So far for textbooks. Let's talk about assignments. There will be, right now in the calendar, there are 7 assignments. If we will not have extra support in gradings, probably will go down to 5 or 6 homeworks. The lowest one out of the 6 will be dropped. As far as the differences between the requirement from the grads versus the undergrads is that you are both getting the same homework, the same assignment, but some of the questions are mandatory for the grads and optional for bonus for the undergrads. Or at the exam has 6 questions, from which the undergrads have to answer 4 and the grads have to answer 5. Differences along these lines. Later in the course, I'll see what the public prefers, and we'll decide if we want to change it in any way to add more research projects, or open, of course, both for grads and undergrads as well, but the grading is different. Other differences are about the mathematical depth that I expect. That we will have, for example, in the case of Voronoi diagram, we will have a long list of theorems, of theoretical results, and of course, I'll tell you exactly what's my expectation, but if you can think about the first theorem, let's call it theorem 1, and it has a proof, and theorem 2 that has a proof as well, and it will be cases where in the proof of theorem 1 we use the proof from theorem 2. So possibly all the students needs to know what the result is for theorem 1 and theorem 2, needs to understand what the theorems are saying, what the theoretical claims that we are making. However, from the undergrads, I'll expect to know what is the proof of theorem 2, to understand the proof of theorem 2, and it will be enough to just be able to cite what theorem 1 is trying to say without understanding or reading the proof of theorem 1, while from the grads I'll expect to understand both cases. That's the type of nuances between the grads and undergrads. Not much differences in as far as my expectation goes. There is no big difference between the groups. It's not supposed to be a too hard course. It's not supposed to be a too easy course. The one promise that I can absolutely give is that the materials that I pick are things that I find extremely cool and entertaining and surprising and important for other domains. So far about the homeworks and the assignments. They will all be theoretical. You have to give an algorithm or explain why this algorithm is correct, or explain how you are using algorithm A to solve problem B, question along this type. I am a big fan of GeoGebra. Maybe I'll show you today why. And GeoGebra, so maybe I'll ask you to submit things in GeoGebra or to use GeoGebra to check some cases, but it's not really a software. It's not really a programming language in any aspect. It's a tool for visualizing geometric structures that is intended mostly for elementary and high school students. And it has also very cute augmented reality app if you want to download it to your phone and watch images in polyhedras floating in your room. Do so, download it to your cell phone and enjoy the geometric, the augmented reality tricks out there. They're very cute. Okay, but mostly homeworks are theoretical. We are all over the internet in terms of the resources that we are using. We use D2L to store the videos and to show you the grades that you are getting. And what else? We are using D2L, Pinapto, of course. You can go to D2L to watch this recordings on Pinapto. At the moment, that's what I remember, and the calendar of D2L. Beside it, I don't think that there is anything that we really need from D2L itself. Please register to Piazza, because in Piazza you can have discussions. I know I could have moved to Discord. I didn't. Yeah, we are on Piazza about discussions and announcements. When I publish homeworks, I'll do it by giving you a link to the LaTeX website that I'm using, which is Overleaf. You have it all in the course website. Overleaf is a GUI that enables you to write your answers if you want to use LaTeX. But even if not, you can just download the PDF. And I prefer to give you the link to Overleaf instead of giving you the PDF, because then if there are questions or clarifications or anything that I want to add to the homework, it's convenient for you to be able to access the online version. I'll give a 5-minute introduction to Overleaf later. Now, when I'm using a Zoom Zoom by itself already for the streaming compress the video quite a lot. And if I'm saving the files, the videos on Pinapto, it is compressed much more aggressively. There is also a few other things that I cannot do in Pinapto if I record to the cloud immediately and I have to upload the files later. So, for example, the resolution of the writings that you see over here will be degraded unless they finally listened to me and decided to change it recently. At least that was the case last semester. So I am tempted also to stream it on YouTube or on Twitch, and save it elsewhere, either in Google, either in my own Google on Google storage or on YouTube, so you can stream the lectures in better quality. Of course, if it's public, then it does not contain your reaction. Your names don't appear on anything that is accessible publicly, which, by the way, reminds me another important aspect. We will have activities like active learning, at which you'll talk to each other, and we'll have rooms that TA and myself will walk around. If they will not be accessed outside D2L, but even for D2L, if you don't want your name to appear on D2L itself on the videos in the discussion, then let me know. There are answers of how to remove your name from appearing. So yeah, these are the resources. We said nGradescope, that's where you submit your homework and see the detailed feedback. You'll do it using Gradescope. So the action list so far is just go and register to Piazza if you haven't so far. Any questions? Bureaucracy at the moment. Okay, I'm not allowed to request it or to demand it, but it's my very own preference. At least at the beginning of the course, I would prefer for the whole course. If you don't mind keeping your camera on, it's I personally prefer it. I think that it's getting you to be more interactive in the course. I can get your face expressions that tells me if what I'm saying is makes sense and understood or not. People are more concentrated if your webcam is on. It's not that when I'm in discussions I don't turn off my webcam and multiprocess, but given how easy it is to lose track in distance learning, it's one of the tricks that I can do to get you still involved. So yeah, at least in our introduction courses, our introduction steps, at least at the beginning, at least in active learning discussions, unless you have some technical reasons why not to, I would strongly prefer you to have your camera on, which also brings me to the whole topic of class participation. So class participation, we are not a big group, and for several, hopefully all of you, I'll have some ideas about how are you as a student in the course, how are you participating, how well are you doing. And to say how well you are participating, it's how much do you talk to me during the class itself? How many answers do you address during the class? Are you actually present in the class? Are you helping in the discussions? Bonus points from homeworks and the midterm and the final. Um, the type of questions that you answered, everything that somehow combined to how are you as students individually, each one of you. You are not going to lose any points if you don't participate. Your grade will not be penalized in any way. But if you look at the grading scheme that you have on the course website, oh yeah, I didn't say it. The course website is actually on Google Doc, as you all know by now. If you look at the grade scope, then if you are getting a 90 and up, and if your grade N is at least 90, then for sure you're getting an A. What happened if you're getting 88? If you're getting 88, I'll have to look at which questions did you answer. I'll take another look at your homeworks. I'll ask, how are you doing as a student? Are you trying? Are you well motivated? Are you participating? Or do I know nothing about you? So 88 maybe is a gray area. 87 maybe is a better example. 87, I keep the right to bump you up to an A, or it can be a B, and it's just basically at this point, at the end of the semester, I'm sitting with the TA, and we are having discussions. What do we know about John Smith? How he or she was doing the course? What his overall activities and the impressions that he made, and how is it comparing to other ones? So at this point, the whole component that consists of class participation, verbally, online, Piazza, everything is in the game, and to help me solidify opinion about you. What else? We will have a midterm and a final. There is a date that I set for the midterm, but we can change it. It should be roughly, we are taking the middle of the semester. From the middle of the semester, we are taking another week or two to rehearse and get answers and go over materials that we discussed in the first half of the semester, and then there is a midterm. And you look at the date of the midterm as it is right now, and you'll think how many other dates or how many other conflicts, midterms, deadline of projects you have. If the class prefers to shift it a bit, I'm game. It makes a bit sense to have it on a Thursday, so Tuesday we are going to have a review, but it's stuff that we can change or not. Okay. Sorry, I meant to have it on, apologies, have it on Wednesday, so Monday we have the review, but we can also have a review, do the midterm on Monday and then over the weekend sometime to have a review, or not to have a review. I think bureaucracy, I think that's the main components. Yeah, let me know if you don't want your name to appear. I don't see the chat at the moment. I killed my chat, so let's see if anybody has any. If you have any questions, I have some sympathy toward vocal interruption rather than the chat as well. Okay, yeah. Thanks, John. Okay, and as you noticed, it's not that I have a lot of that as streaming slash software to handle a few screens. I think that OBS has some advantages over Zoom directly. So I broadcast, I edit, I'm trying at least to edit with OBS and create a virtual camera that I send to Zoom and also record directly from OBS. Both higher quality as well as giving me more flexibility about the part that you see on the screen. I'd like to use both electronic board and physical whiteboard. I still think that physical whiteboard beats other, has a lot of advantages. Details, if you're watching the lectures only on cell phone, details are seen, but it's a bit small. I'm checking myself with my cell phone as we talk and with my iPad. I'd recommend that you'll use a tablet or a monitor as well, because to see all the details that things might appear too small. So it's but also make noises and please be assertive if you don't see details out there. If things fonts are too small or recording is bad, etc. We talked about several types of media that we are using, which was, as we said, Piazza, D2L, Overleaf, Gradescope, etc. There is also Google questionnaire that I'll send you right after this class. The Google questionnaire is something that gives me idea during the course itself about what do you think, what do you see as a problem. It's what do you prefer, what do you like, what would you suggest to correct, what do you hope to have in the course later down in the course. I don't know if I can prove it to you, but I don't have any way to see who filled what. It's completely anonymous from my side. Google will ask you for a password just so you can later go and edit your comment. Like you saw, you had one suggestion and then you see another suggestion, or one complaint and another complaint. Then Google will use your login to enable you to edit it. However, it's completely anonymous from my side, and it doesn't play any formal role. Like it doesn't go to my dossier, it doesn't go to my TCE evaluation. It's just a way for me to communicate with you in a way that doesn't ask you to reveal your name. Like just anything that you want to tell me anonymously, we will use a Google questionnaires. I'll send a link via the course website and via Piazza shortly. What else bureaucracy-wise? I'm sure that I forgot something. Things will come up. A question that appears after every homework and every exam. In many of the exams, you can get grades that is higher than 100. For example, you'll see that the sum of questions sums up to say 108. And if you see the grade 108, the other camera, if you see the grade 108, you shouldn't think about it as 108 divided by 108. It is not being normalized, nor or it should not be considered as a 108 for the final course calculation when we are computing the average. The way you should understand the 108 is that, or what we stored from the 108 is that you got 100 normal points plus 8 bonus points, and that's how I treat it later. And what's important of the 8 bonus points is that it goes into my overall appreciation toward you, this opinion of class participation. And if you later ask me for recommendation letters for universities and workplaces, or it's definitely the first point that I'll say. Like 20 or to 30% of you will probably get an A. That's a normal grade distribution that I have. It is somewhere between 20 and 30 normally. So somebody asked me to, and later you ask me for a recommendation letter, and I'll first see, let's say that you got an A. I'll say I can write a relatively, partially lame, not that exciting recommendation letter that says you got an A together with 20% of however many people we will end up with. Or I can say that you were one of the best students because you were the one that was solving the hardest question and you did all these extra works and took and you were the only one that solved the challenge question, that etc. Something like this. So that's where these 8 points are computed. That is, I'm sure that I'll say it later in the course, but once again, the 108 that you'll see in the end of on your homework 1 might be 100 normal points that are used for the calculation plus 8 bonus points, which means that if in your next homework you are getting 20 plus 0 bonus points in homework 2, then your overall average in these two homeworks is 120 divided by 2. It's not 128 points divided by 2. That's for the average, but of course. More bureaucracy. I have a funny weight distribution that I'm using for the last 20 years that look at your midterm and you look at your final exam score, and it gives more weight to the better of the two. Again, between the midterm and the final, the one that has higher grade also gets more weight. And the intention behind it is that if you did poorly in the midterm, but you want now to pull yourself together and did fantastic for the final, then you still have a chance to get a good grade, provided that, of course, you'll do much better towards it. And vice versa. You did fantastic in the midterm, but you had 3 other finals in the very same date. You did poorly. The final still has significant weight, but less so than the midterm. So I think that it's kind of systems that impose some level of optimism, giving more weights in this part. Okay, that's what I can think about at the moment about majority of the course. Let's start with the academic part, where in the course we will talk about the introduction. What am I going to do in the introduction? I'm going to review big O and big omega that you have seen hopefully in 345. If you didn't take 345, you can still do fantastic in this course, but a few basic topics you can probably cover yourself, but you have to be a decent and motivated student to do so. And let me know if you did not do well in 345, and I'll tell you what the little tweaks that you need to do. However, I'll mention to you in the introduction what are basic complexity, what is big O, what is big omega. I'll do it very quickly, and then I'll pick a few problems that computational geometry is looking at, for one of the big spectrum of computational geometry topics, I'll especially pick on convex hull problem because it's computing convex hull is a problem that has many algorithms to do it. It's a good way to highlight some of the basic paradigm of algorithms in general, not only geometric algorithms, but the whole world of algorithms. There are several main approaches of how do we tackle problems. Should we try to look at the input to our problem and divide it into two sets and solve each one independently and then somehow merge between the two, which is a famous divide and conquer? Do we try to solve the problem by picking 3-4 elements to start with and then adding one extra element once in a time and keeping the solution after each element? Another example, and so on. So convex hull will play a bit at the beginning because it's a good way to be more concrete about what's happening in the course, some tweaks, as well as explaining some fundamental concepts of algorithms and complexity as a whole. Things that you've seen in 345, things that you have seen in probably 245 as well, or in any introduction course that you took in data. I'm especially referring to grad students that might took your undergrad in other universities. If you took data structure course, then you've probably seen related things that will help you feel getting warm and fuzzy feelings about topics in the introductions. I'll also mention a few of the many problems of computational geometry. Together with it, I'll speak about some of the very basic techniques that are transferable to many other problems. We will talk about basic data structures. Data structures plays a big role in computational geometry, the basic ones of how do we represent surfaces, how we are representing maps and partitions of the space or the shape into elementary units that we can work with. People that took graphics with me or elsewhere will see a lot of familiar terms when we talk about basic data structures. We will talk about polygon triangulations. Some cases of it we'll spend a lot of time about polygon triangulations and triangulations of surfaces and of surfaces on set of points. Quick example: I laser scanned my arm, or people, or my arm. Somebody gets the shape of my arm from an MRI or from laser scan or whatever other imaging device. There are now a lot of points in three-dimensional world representing my arm, and you'd like to somehow connect these points in a meaningful way to describe the shape of my arm, so that now you can make a statue out of it after later on. So you can send it to the your graphic software or your graphic monitor or your animation program to or your 3D printers, and you'd like to send a surface that is usually triangulated surface, but there are a lot of ways to have a very bad triangulations or very bad representation of the skin. We would want to see ways to do good triangulations. So we'll talk about triangulations quite a lot. I'll probably mention linear programming. There are a few beautiful and ingenious algorithms that handled linear programming, and linear programming is also one of the topics that you cannot go wrong by talking more about it. There are extremely powerful tool in any problem, mostly optimization problems, but also in machine learning, in linear classifiers, in feasibility, in resource allocation, linear programming, transportation. It's one of the techniques that, if not with me, own it to yourself to know what is linear programming before you are out there to the big world. So we'll talk about linear programming and some of the contributions that computational geometry did to linear programming as a whole. We'll talk about range searching. I have a lot of data from geographic information systems, GIS, and I want to, I have the populations of all the cities in the state, and now I want to ask who lives in some region, or how many people lives in this region, or if I'm in game design and I am saying that I just teleported from one point to another, who is the other characters that are near me, or the obstacles near me. Voronoi diagrams, I'll mention today what they are. Extremely important tool. Hopefully we'll talk more about duality and arrangements. Beautiful results out there. Together with the Voronoi diagram, we'll also talk about Delanoy triangulations. Well, one type of triangulation that is like the universal answer. It's like saying 42. They ask you, how do I generate good triangulation? And you're asking for which purpose, and somebody tell you what's the purpose, and your answer will be, oh, if that's what you want from your triangulation to be, then use Delanoy triangulation. And the next day somebody asks you, I need a triangulation for extremely different purpose, which triangulation should I use? You'll still say Delanoy triangulation, because it's doing many good things all at once. Maybe I'll talk about computer graphics application. Maybe I'll talk about sensor networks applications. A lot of people, including myself, realize that they can bring things to computer, to networking and geometric networks and sensor networks and fiber networks using computational geometry tools. It will be a good motivation. We'll talk more about applications to machine learning, obviously, graphics, computer vision, robotics. We'll see examples of problems from all over. People, any questions so far? You're very quiet, and you also don't keep your camera on, at least most people. Anybody? Anybody's alive? Yeah, I know that asking you to keep the camera on all the time is a bit annoyance, but uh, it's my own 2 cents is that meetings that I keep my camera on, I concentrate more. It's so I will try to extrapolate it to you as well. And of course, we will try even in this um, distance learning atmosphere to do group discussions, and then definitely having the camera on is would be even more important. Don't remember if I said it in the website, by the way. We'll use Examity, where you have to have a webcam working for the midterm and the final. Okay, what are we going to do today and probably next meeting? A few problems to give the gist of the fundamentals of computational geometry, some basic concepts, and a few of the simple convex Hull algorithms. So let's start with the question of nearest neighbors question. What is the problem? We are giving a set of points, each one of the orange points. We're giving a set of points, maybe in the plane, maybe in higher dimensions. The higher the dimension is, the harder the problem is. These points might be geometric objects to start with. Maybe they are players in your team. Maybe it's location of hospitals, as we'll see soon. Maybe they are geometric parts, or maybe each one is a measurement that I did using a few sensors, and when I used the x coordinate for, say, the temperature, and the y coordinate to denote the time, or that's the weight and the age of an animal that I just checked, or whatever it is. So every measurement will be another coordinate, another parameter that I can assign to each such data point. And now, after I looked at all my players, points, graphics, sites, we'll refer to them as sites in the plane. Now you surprised me with a query point. And this query point, Q for query, it was not part of the original point. Now you surprised me with such query. Before you gave me actually the query, I had the time to relax, leisurely build structures for all the points, invest some time for it. And now Q, the query, appeared, and you want a really prompt question: who is among all the original points, the original yellow sites, who is a site that is the closest to Q? Who is the site that is the closest to Q? Closest in what sense? I can measure the distance using Euclidean distance, for example. Euclidean would be what you think about Pythagoras theorem, the difference in the x square plus difference of y square root of all of it. That's just Euclidean distance. Or I can ask, as Amir, one of the students sitting among you, is doing, asking about points that have that lives in a city, and I know about the city, what is the velocity of each street, what the maximum velocity of each street, and what maximum velocity of walking and traffic average speed. And the distances are more involved. The distances might be the time proportional to the time that it will take me to get from Q to each one of the sites. But I don't need to know the distance from Q to each one of the sites. What I want to ask is, once the query point Q has appeared, I want to ask what of all the sites, what out of all the sites, small p in P, is the closest to Q. if I think about the site as hospitals, I want to ask who is a hospital that it will take me the minimum time to arrive to. That will be the nearest to one, that's the nearest neighbor. Possibly the answer is this site by itself. Possibly the answer is unique. Possibly the answer will say there are two sites which are equidistant from you, but the distance, the sites to each other point is larger. So that's type of nearest neighbor queries. I'll state it as in the rule as one point sets, one set of sites. And now you gave me this query and I want to be able to answer your query really quickly. Why do I want to answer this query really quickly? Probably because it's not a single query. You have a lot of query points that you are planning to bombard me with. And for each one of them, I need to provide the input right away. So I want to spend more time building structure for the original set of sites so that each query point I can answer quickly. And there are plenty and plenty of applications to this type of queries. You can ask which is the store that is the closest to me. You can ask Q is one of the cell phone users, and Q generates a lot of queries because Q is actually walking down the street, and each time I need to ask what is a cell tower that is the nearest to Q. Okay, many applications. Let's already introduce you to one of the really fundamental concepts of computational geometry, of science in general, but computational geometry, named after a Russian mathematician that unfortunately I don't remember his first name right now, and this is a Voronoi diagram. What is a Voronoi diagram? As before, I have a set of all the sites, all the hospitals sites in the plane. Here is hospital P1, here is hospital P2, P3, P4, and so on. After I thought about all these sites for a while, now I want to create and I want to answer queries to answer some queries, but I want to do it in a more systematic way. I want to see what structure this set of points imposes, and I want to define what is a Voronoi diagram. So we'll first describe what is a Voronoi diagram in mathematics crypto, which would be very formal but hard to decrypt, and then we'll explain what we really mean. What I want to do is to generate a planar subdivision of the plane. I want to take the whole plane and chop it into cells. Here is one cell. This cell actually goes to infinity. Here is one cell, this polygon here in the middle, this cell that somehow centered around hospital P2. Here is a cell of P3 and so on. So I want to break the whole plane into cells, generate this subdivision of the plane called planar subdivisions, such that each one of the sites, the hospital, will have its own cell. P3 will have a cell that looks like here. P2, we already talked about its cell. And what is the importance of these cells? Well, a point, typo, just 1a, a point Q will lie in the cell of some hospital P. Remember, P are the hospitals. What does it mean that Q lies in the cell of P of P2? It is because out of all the hospitals, P2 is the nearest hospital to Q. So the cell of P2 are all the points in the plane that will say out of all the hospitals, P2 are the nearest hospital to us. The cell of P1 are all the points which will say out of all the hospitals, P1 is the nearest hospitals to us. A point lies on the edge between the cells. If you guess where it's going, a point lies in the edge between these cells of P1 and P2. Why? Because it is any point on this boundary, on the edge between them, says my distance to P1 is the same distance as my distance to P2. Every point on the edge is equidistant from P1 and P2. And oh, by the way, any other hospital is furthest away from me. P1 and P2 are my two nearest neighbors, equidistant to both of them, and every other site is even further away. And you can guess what is a vertex, the meeting point of three edges. What is a vertex? This, let's pick this one so I can use name. What is this vertex over here? How well do you see my mouse? I think it's visible. The vertex here in the middle is equidistance between, so that it has the same distance to P3, P2, and P1, and the distance from this vertex to any other hospital is even further away from it. So where are we using Voronoi diagram? In what applications beyond computational geometry do you have? Millions. Google for Voronoi diagrams. But here is one of them. I'm using supervised learning. Somebody gave me examples of animals that I checked in my lab. I'll say that the x-axis is the weight of the animal, the y-axis is the height of the animal, and every red point happens to be a dog, every orange point happens to be a cat, and again, the x and y coordinates are just the weight and the height. And now you asked me about a point Q, which is an animal that you are not sure about. Is this a cat or is this a dog? That's what your classifications need to do. And I'll tell you, based on just the weight and the height, I'm not sure, but let's see, we have a lot of examples that are already labeled. All the points that you see already, these are not hospital in this case. These are animals that I know already if they are dogs or cats. So what should I do? Or what's a common nearest neighbor algorithm will do? It will say, tell me what is the animal that is the closest to Q. And if it is a dog, then I'll say that probably Q is a dog. If it's a cat, I'll say that Q is probably a cat. That will be by finding the single nearest neighbor. Or you can ask, find from Q what is the first nearest neighbor, what is the second nearest neighbor, the point whose distance to Q is not the minimum but the second smallest, maybe the third minimum. So for Q it will be this point and this point and this point. And I'll say out of these three animals, let's look at the majority. The majority are cats or the majority are dogs. And that will be our classification of Q. Very common, very practical methods to predict behavior based on examples, based on supervised learning. So here is where nearest neighbors are used any time that you need your computer to make decisions or predictions. Questions, people? Okay. Point location, I mentioned it briefly. In the previous slide, I built the partition. What do I mean I build the partition? I told you what are the boundaries. I told you here are the edges, here are the cell, the faces, here are the vertices. Now, after I created this boundary, I know how the plane looks like. I want to do efficient point location. Namely, here is a Voronoi diagram, and here is my point P. Now I'll use P for the query, not for the hospital. P just landed, just parachute, and during the parachuting got injured. He needs to go to the hospital. In which cell does P lies, so that I can know what is the nearest hospital? You just appeared on the map. Where are you on this map, in which state, or in which room if the structure is not two-dimensional but three-dimensional or even higher dimension. They want to do point locations application, and we'll talk about it. I can check each one of the cells to see if P lies inside it, which even this is interesting question. But this will mean that I need to check each and every cell until I find the one that contains P. I'd like to have an answer not in linear time, but in logarithmic time, or at least much more efficient than check each cell exhaustively. For P in this case, this will be the cell, this is the answer. So the rule of the game is after the input is a partition, for example, the input is a Voronoi diagram, and you're bombarding me with a stream of a lot of queries, and for each one of them I need to ask which cell you are, because once you know at which cell you are, I can know what is the nearest neighbor. Just one of the many applications that you can have out there. And other applications, anybody but Amir sees application from graphics? We will start, or maybe somebody is trying to talk and I don't hear you. Zoom preference, test speaker. No, the problem is not in my speaker. You guys are too shy. Sure. In computer graphics, where will I need point locations? Again, point location would be, I told you about some geometric graphic scenario. There is a room, there are obstacles in the room, there are chairs and tables and walls in this room, and I bombard. And after you think about this room or this geometric setting for quite a while, I tell you about a point P, a query point, and I want an answer really quickly. What is a cell that contains P? Of course, it can be in game design. You just teleported and you need to show the player at which room it is. In graphics, it might be that P is actually the result of a ray shooting, that you want to ask at which color do I need to render a pixel that corresponds to a ray that just hits the wall at P. If my ray if my ray hits a red object, then based on where the point is, I can say this object is red, which will mean that the corresponding pixel that corresponds to this ray should be rendered as red. And had the ray hit the blue pixel, of course, the answer should have been it's blue. Tell me, by the way, how do you guys like this arrangement of two cameras and slides? Does it work for everybody? Is there any problem with this? I didn't try it before. Okay, cool. And as I said, the recordings will be of higher quality, and and there are two recordings, as I said, one that contains everything that concentrate on me only, the way I like it, and one that and the D2L that contains the normal Zoom recording, including class participation. Okay, you landed in a map. Find where you are, at which country did you land. That's point location queries. But you notice that we had countries or states earlier, and I want to ask, hey, a point Q, are you at all inside the room, the cell that called P, now P for polygon? I told you about the boundary of the room. Let's keep it 2D. So the boundary of the room are just the walls. And I want to ask, is Q, my query point, lies inside this room or not? And the answer is a bit tricky. We'll talk about it in the homework, but it's more technical if P is convex. What is convex? Convex meaning exactly what you're intuitively thinking about convex, in the sense that this shape is convex, this shape is convex, and this shape is not convex. We'll talk about formal definitions that will come up later in the course, but to answer if a point P, Q lies inside the convex polygon P, if you allow me to do some binary search on the edges of P, I can answer quite fast. Fast here means log n time, where n is the number of edges. But a much cuter question is that what should I do if the polygon is not convex? Convex, as I said, we'll go back, but here is Q, and I was a bit in a hurry. I could have drawn Q, the polygon Q, which is not convex. By the way, non-convex doesn't mean that it's concave. Two different things. It's non-convex and I want to ask, is Q inside the polygon or not? And can somebody outline an algorithm for it at all? It's you Yep. So just want to say, it's by checking Q locally, especially if I just draw its boundary, it's really tricky to say, I know that it's near the boundary, but is this from the outside or the inside of the boundary? It's not clear. It's not clear at all, and nothing locally by just looking at the edge that can reveal to me exactly the truth. Is Q is inside or outside? Of course, it's looking confusing this way. Of course, the moment that I paint Q, now Q is of course orange and it's quite clear, but algorithmically there is a really cute trick that helps me decide if Q is inside or outside the polygon, and that's how it goes. I'll draw a vertical line. It's actually it was enough to draw just a ray, but let's shoot from Q, this point over here, a vertical line that goes all the way to infinity. This vertical line goes far, far away, and it is quite easy to check. We'll see exactly how, but it's quite easy to check if an edge of the polygon intersects this vertical line. Then I can look at one edge, I can look at one vertical line. Each one of you can write down in about 20 minutes, much less, a program that checks if the vertical line crosses the edge or not. Especially since the line is vertical, all you need to do is just to know what is the x coordinate of this line. There is no y coordinate, and then you're just checking if the edge crosses it. Just means that there is 1 point to its left with smaller x value, 1 point from its right. It's to a larger y value. So now once I can check what are the edges that crosses the vertical line, I can do the following mental step. I can start up there, leaving at the sky, leaving at infinity, and I'm sure that I'm outside the polygon right here when I start my way far, far at the bottom. I'll go all the way to infinity, so I'm outside the polygon. And now let's start falling down until we are hitting the very first edge on our way. Now when we cross this edge, I'm sure that I'm inside the polygon because the edge is a boundary to separate being inside from the outside. After I hit the first edge, I am inside. Keep on following, I hit another edge once again. That means I exit the polygon. Another edge, entered, exit, entered, exit. Eventually, I just checked when I reached Q, did I cross an odd number of edges or an even number of edges on my way from infinity all the way to Q. So it's kind of cute, no? That that it's all about the whether this about the parity of the number of intersection points that you have along its way. But that's already a good example of why general position assumption makes life easier. General position is like no Murphy law. There are things that are very unlikely to happen, will not happen. What do I mean? In this little problem, how could I have bugs in this algorithm? What happens if my vertical line here is Q on the whiteboard, and here is my vertical line, and it just crossed both edges E1 and E2. So does it mean that if I'm falling down along the vertical line, did I enter Q or did I not enter Q? If I hit a vertex, should I count it as 0? Should I count it as 1? You see the problem. I should count it as 1, but that means that E1 and E2 cannot be both treated the same way. Otherwise, I crossed two separate points. So you see, that's the type of headache that makes a very simple and elegant algorithm into a bit less elegant and need to have more ifs condition and more side cases to make it completely robust. And that's, by the way, the reason that a lot of people makes fantastic money from having companies that takes relatively simple algorithm but implement them in a way that numerical issues and robust cases you don't cause your program to malfunction and doesn't cost you, for example, to send an object to your 3D printer where you are confused about what is the inside and what is the outside, and which will mean that suddenly your 3D printer only printed a hollow shape where you hope to have a solid. People, questions? Slightly over time. Any questions? Bureaucracy or syllables or anything else? Fantastic. Yeah, sure. Sorry, I'll have my office hours and Jacob will have office hours. Yes, yes. Everything is based on Zoom. Yeah, here. Nothing happens. Okay, I understand the question. Yeah, it's a current situation. We'll stick to Zoom and social distance until we have further news. I'll place it. Thanks for reminding me. By the way, people, please don't assume anything that I know or that I understand or that I ignored. Give all the credit to my ADHD and my carelessness, and don't be shy to re-mention something more than once. For example, yes, I will place a Zoom link or either in Piazza before the meeting, or will use my personal link that is in my we are using for the class. Superb. And yeah, so there are 2 hours that I specified, and I am also scheduling now in Kronos time is so much easier. Since I don't have much plans for the next half a year or so, yeah, if you want to meet outside the office hours times, usually I'm very happy to. Thanks, everybody. Later. Bye.